In this video, we are going to cover the basics of galvanic or voltaic cells. Hopefully by the end, you will have an understanding on how these devices work and how to draw them, which will be the foundation of this topic. And then in the next video, we'll go over some more nuances that you might encounter in, let's say, an exam. So first, let's try and demystify these terms here. Galvanic just means able to produce electricity. And cell, in this case, just means a device. So galvanic cells are just special devices that produce electricity. And if you're watching this on a laptop or an iPhone, you may be surprised that they actually have galvanic cells inside of them. But that's probably because you know them better as batteries, which is just a type of galvanic cell. So how do batteries or galvanic cells work? Or in other words, how do they make electricity? Well, they do so by using chemical reactions that release electrons. So chemical reactions, which involve chemical energy, is just the energy stored in the bonds of molecules. And this is then converted into electrical energy, which sounds similar to electrons. And that's because electrical energy is defined as the movement of electrons in a circuit. So if you have electrons moving in a circuit, then you'll have electricity being produced. And this energy transformation from chemical to electrical is what defines galvanic cells. Now that we have a basic understanding of these galvanic cells, let's try and piece one together. And I'm just going to draw one type of galvanic cell, so don't worry if you've seen different images in your textbook. First, we are going to draw two large beakers, which will form our half cells. And one way to think about it is that each beaker is half of our entire galvanic cell. Next, we are going to fill each beaker with some zinc nitrate and some copper nitrate solution. And these two solutions are known as our electrolyte. And if you look at this word, electro is related to electricity. And this is because when we have our solutions, such as zinc nitrate, dissolving in a solution, it produces zinc 2 plus ions and nitrate or NO3 minus ions. And we know from before, if we have charged ions moving around, then there's potential to conduct electricity. So hopefully that helps you remember what electrolyte means. Then we are going to add in two pieces of metal, one piece of zinc metal, and one piece of copper. And these are called our electrodes. One electrode is the anode, and the other one is the cathode. Now these electrodes, or pieces of metal, is where our chemical reactions occur. And to be specific, these chemical reactions are called oxidation and reduction reactions, also known as redox. Now, what's special about these two pieces of metal? Well, one of them really wants to get rid of its electrons, and one really wants to gain these electrons. It's kind of like when you want to buy something off of someone else. You want the thing that you're buying, and the person you bought it from was happy to give it away. Only in this case, we're talking about giving or receiving electrons. Okay, but how do we know which piece of metal wants to give away electrons? That's where we need to use something called the electrochemical series. Okay, remember that the two we used in our cell was copper and zinc. So I've highlighted both copper and zinc on my electrochemical series in red, and I've just rewritten the chemical equations on the left here. Now, how do we tell which way the reaction is going? There are many ways to do it, but the one I use is called the backwards Z. If you take the letter Z and flip it on its side, you get a backwards Z, and if you put arrows on the ends, it tells you which way the reactions are going. So for copper 2 plus, that is gaining 2 electrons and turning into copper solid. And for zinc, it's zinc solid that's turning into zinc 2 plus and 2 electrons. Now, to do this, the reactions must be in the order of the electrochemical series. So I have to have copper above zinc. It's just important to note that the anode is defined as the site of oxidation. So it's the place where oxidation is happening. And remember from redox that oxidation is the loss of electrons. And then in contrast, for the cathode, that's the place or electrode where reduction is happening. And reduction is the gain of electrons. So we can see that copper 2 plus is gaining 2 electrons. So gaining electrons means reduction. So copper must be the cathode, because cathode, that's where reduction occurs. And then for zinc solid is losing electrons, which is oxidation. So that means zinc must be the anode. And each of these reactions are called half-cell reactions because they represent half of what the entire reaction would look like. Now that we know this, let's go back to the diagram and just label it. Okay, now that we've done that, we need to connect these two half cells together. And we do that by connecting these two electrodes with some conducting wire. And that way, the electrons can move from the zinc anode to the copper cathode. And that's something important to note, that the electrons always flow from the anode to the cathode. And you can understand this by seeing that at the anode, electrons are being released. So zinc is turning into zinc 2 plus and 2 electrons. So it's releasing 2 electrons, and that's why electrons flow from the anode to the cathode, where electrons are being consumed by the Cu2 plus. So now, one of the most important things that we need is a salt bridge, which is just a device that balances charge. Now, I want to cover why this is even important in the first case, by using a cleaner diagram. Now, let's see what happens to the galvanic cell when zinc and copper start reacting. And we can look at our half reactions to give us a clue on what's happening. Starting with the zinc half cell, we have our zinc electrode, which is made up of solid zinc atoms. And as this reaction progresses, these solid zinc atoms turn into zinc 2 plus aqueous. Since we have solid zinc dissolving away, this means that the electrode here is getting smaller and smaller over time, because solid parts of this electrode are breaking off, dissolving in solution, and releasing their electrons. And another thing to note is that if you look at our reaction, we are turning solid zinc, which has no charge, into zinc 2 plus, which has a charge. We are making this solution more and more positive as this reaction progresses. And before I explain the implication of this, let's have a look at the copper half cell first. So if we look at the reaction, we have copper 2 plus reacting with 2 electrons. So the copper 2 plus is found in our solution, and the 2 electrons were released by the zinc from before, and they travel around the wire to the copper electrode. And what happens then is that the copper 2 plus and the 2 electrons react at the surface of the copper electrode, and it forms solid copper. And what this will look like visually is that you will start to see this lump of copper forming on the electrode. So unlike the zinc electrode, this electrode is becoming bigger. And also, the copper 2 plus ions are being consumed, so they're being reacted away. And if there's a loss of positive ions, what that means is that the solution is becoming less and less positive. So in other words, it's becoming negatively charged. Or you could say, since electrons are being received at this half cell, there is going to be a buildup of negative charge. Since electrons are negative, so if there's more electrons here, then the half cell is going to be more negative. To summarize, we have the zinc half cell becoming more and more positive because of the production of positive ions. And the copper half cell is becoming more and more negative because of the loss of positive ions. And this is significant because if there's a buildup of charge, these two half reactions stop happening, and the galvanic cell or battery no longer works. So how do we solve this? We do so by using something called a salt bridge. And as I mentioned before, this salt bridge works to balance the charge. And a salt bridge can come in many forms, but it can be as simple as a piece of porous paper dipped in some ionic solution. So, for example, a very common salt bridge that we use is potassium nitrate. What that means is in our piece of paper, we have potassium and nitrate ions, and they are free to move. And we put this piece of paper so it's in contact with both solutions. Now, the ions in the salt bridge are going to move in a way to balance charge. Because opposites attract, since copper half cell has a buildup of negative charge, the positive K+ ions are going to migrate towards that half cell. And then likewise, since there's a buildup of positive charge in the zinc half cell, we're going to have the negative nitrate ions from the salt bridge migrating towards the zinc half cell. And what this process does is it works to balance and neutralize the charge. And as you can see, anions always go to the anode and cations go to the cathode. So that's another way that you can remember it. Anode, anions, cathode, cations. Now that we have the salt bridge, that is pretty much the entire galvanic cell. So let's return to the annotated diagram that we had at the beginning and just add in the new parts. And in addition to this, you might also see something along the wire here. So usually a voltmeter or a light bulb. And the purpose of these things is to make use of the electricity. So whether that's lighting up a light bulb or measuring the amount of volts, that's why we usually have something attached along the wire. So to summarize all the main parts, I came up with this acronym. So it's called CASHU. So you can see that the C stands for cathode, A stands for anode, S for salt bridge, H for half cells, E for electrolyte, and W for wire. And you can see all these parts on the diagram on the right here, which is color-coded, as well as some additional information that we covered in this video. So you can use this as a checklist to make sure that you remember to draw these cells correctly, because they definitely can be hard at first. Okay, so this has been an introduction for galvanic cells, and in the second part, we're going to cover some more intricacies for each part of a galvanic cell. So if you're interested, I'll see you there.